In this video, we're going to go through the 2024 double award higher paper. I've put the grey boundaries on the front so you can work out how hard this paper is. The first question is asking us about power stations, and the first thing is the payback time. So we do need to memorise the equation for payback time. So it's the installation cost, which is usually quite a large number, and we divide that by the savings per year. Occasionally it's savings per month, but it's usually the savings per year. So here our installation cost, so that's how much it is to build. It's this large number, 38 million, divided by the annual savings, 3.75 million. And your answer would be 10.1 years. It does say to accept 10 years, but make sure you type this in carefully into your calculator and that you round it correctly, or you could lose a mark here. You can also get 1 mark for your equation if you did the equation right but got your answer wrong. Second part, state one reason why the payback time could change. So first thing is that the cost of the electricity could change. But instead of electricity, you could say energy, you could specify the wood or the biomass could change. But you could also say the amount of energy they use, so the energy use could change as well. Both of those would affect the payback time. Part B, Sarin states burning wood produces CO2, so it's harmful to the environment. Explain whether you agree. So the important thing to notice here is we are using biomass. It's not one of the fossil fuels, so when biomass grows, it absorbs CO2 as well. So you want to state that. So growing trees absorb CO2. And then we want to say the same amount of CO2 is released when it's burnt. So mostly you're going to be disagreeing with Sarin because it's not harmful to the environment because it absorbs the same CO2 as it releases. It's carbon neutral. Our next page has got a Sankey diagram for that same biomass power station. It's a little bit complicated, so I'll go through it. This is our input. This is our first electrical output. Then there's some heat. Some of it is waste heat, so we can't use it, and some of it is used in our factory, so it's still useful. So the first question is to work out the total useful power. So the electrical power is useful, and so is the heat because we're using it as useful energy. Not necessarily all heat is waste. So we're just going to add these two up for the first mark. So 3 plus 13.4. Always write your working, just in case you make a mistake. 16.4 megawatts. Evan states it's only 15% efficient. Do you agree? So first of all, I would look up your equation for efficiency. It's the useful divided by the total or the input times 100. So our useful we've just worked out is 16.4 divided by 20. They're both in megawatts, so we can ignore it. And then we times it by 100, and you should get 82%. And it does say, do you agree? So we're going to say we disagree. It's much more efficient than that. This is another question that's very important to do your workings, because if you got this one wrong above, but you used it here, you could still pick up marks. But if you didn't show your workings to show where you got the wrong answer from, you wouldn't pick up any marks at all. This next page is all maths questions. Again, show your workings because they all lead on from the one before. So if you don't show what numbers you used, you could lose marks even if you've done the correct method. So part D, the input power is 20. Use an equation from page 2 to calculate how much energy is transferred by burning wood every 60 minutes. So we are looking for an equation with energy. This is watts, so this is a power, and we've also got a time here. So we're going to look on our equation sheet. Energy is equal to power times time. So our power is in megawatts here. However, our answer's in megajoules, so I can ignore that because they'll cancel each other out. If you don't understand why it is that they cancel each other out, you can use the conversion for megawatts and then convert it back at the end and you'll get the same answer. We're then going to times it by the time, which is 60 minutes. But when we're working to work out an energy in joules, we do time in seconds. We've also got to times it by 60 again because there's 60 seconds in a minute. So you'll be doing 20 times 60 times 60, or you could have shortened it and done 20 times 3,600 if you did just 60 times 60 separately, and you should get an answer of 72,000 megajoules. There are lots of other places you could have picked up marks in this question if you got different answers. So there was 2 marks for 1,200 and 2 marks and 1 mark available for some other answers. Same as if you got the wrong amount of zeros here, you tend to get 2 out of 3. This next question links to the one before. So burning 1 tonne of wood produces 2,880 megajoules. Calculate how many tonnes of wood every 60 minutes. So the one before was 60 minutes as well. So we don't need to worry about that time anymore. It's just saying it links to the energy we worked out before. So what we do is we take our answer from the question before. That's how much total energy. And each tonne produces this much. So that means to give us that end amount of energy, we must have burnt 25 tonnes. And you can check that if you want by doing 25 times this number will give you the total amount of energy. Okay, the third part here, we are using volume is mass divided by density to determine how much wood is burned every 60 minutes. So we're going to take the mass from the question above, 25, but that's in tonnes and we need it in kilograms. So it's told us 1 tonne is 1,000 kilograms, so we times it by 1,000, and then we divide it by the density that it's given us, divided by 500, so you should get the answer of 50 metres cubed, and you'd get this mark, at least 1 mark, as long as you used your answer from the one above. And then the final part on this page, an average tree produces 5 metres cubed of wood. Calculate how many trees are burned every 60 minutes. So again, we take our answer from above, 50, and we divide it by 5, and that means we've got 10 trees burned every 60 minutes. Okay, question 2 is our 6-mark question, and this is a very common 6-mark question. It's asking us to measure voltage, current characteristics of a device. And here it is a 12-volt filament lamp. So this is our filament lamp. And this is the results that our practical should give us. So part A is explain how we use the circuit to produce the results shown, include what components they need to add, how they're connected, and which method they use to get several pairs of readings. So first thing I've done, I've drawn them on the picture as well, but I would write them also. I don't know how they mark this question. First thing you want to do is connect your ammeter in series, and I've specified that, to measure current. It's a 6-mark question, so you want to prove how much you know, and you know an ammeter measures current, so make sure you state it. In series just means next to, so it could be here, could be up here, could be down here, doesn't really matter. The second mark would be connect a voltmeter in parallel. So this is what parallel means. It means across something with 2 wires, one each side, so it can compare the difference, and that measures voltage. Then we've got our method marks. So we adjust the variable resistor to its maximum. That gives us the lowest value of voltage. There we will record both the voltage and the current. So that will give you one of these low marks down here. Then we adjust the variable resistor in increments, and we repeat these steps until we get a full range of results, and we collect it up to 12 volts. We know it's 12 volts because the question tells us. Sometimes I'd add a step and say repeat with the bulb the other way, but they haven't done that. We can see on our results there's no negative values, so this is enough. Make sure you've learnt some variation of this method because it does come up every year. Part B is using the graph that shows the results on the right-hand side of the previous page. George states the resistance of the lamp decreases as the voltage increases. Do you agree? So first mark that I would try and do here is describe what is going on in the graph, which is that it's showing current, not resistance, and the current is increasing at a decreasing rate. So the current is still going up as the voltage goes up, which is what we'd expect, but the higher voltages, it doesn't go up as much as we would expect. That is because the resistance is increasing as it heats up. So our second mark is saying this shows an increase in resistance. You might also want to say, for good measure, that we disagree with the statement George has made. Question 3 is on circuits. So the circuit shown below contains two identical resistors in parallel and each has a resistance of 10. So the first thing we're going to do is calculate the total resistance of the circuit. It's in parallel, but it has given you the equation. So first thing we'll do is we'll write this out with the numbers in. 1 over R total is 1 over R1, so that's 1 over 10 plus 1 over 10. And we can even write on, these are 10 ohms onto our diagram, so we can use them later if we need to. So this first bit should give you an answer of 1 over 5. You would get 1 mark for that, or if you'd written it as a decimal, 0.2. However, that is 1 over R, not R. So we need to flip our fraction, or we do 1 divided by our previous answer. Only do one of them, and we'll get the answer of 5. That is our total resistance. Next, when we're looking at current, so we've got a voltage as well up here. So I'm just going to write down what we have. We've got a voltage of 12 volts. We have a total resistance of 5 ohms, and we're going to use that to work out our current. So the equation we're going to use when we check our equation sheet on page 2 is V divided by R. So we're going to do 12, because that's our total voltage, divided by 5, or whatever answer we got on the previous question. That's why it's important that we write down what we're doing, and you should get 2.4 amps. I'm going to add that again to our drawing with an arrow to show its current to help later. On to the next page, I've copied across the circuit so we can use it still. First one, state the voltage across R2. That's what our voltmeter here we're measuring. It's a parallel circuit, and if you remember, voltages in a parallel circuit stay the same. So that's just 12 volts. It would be 12 volts across here, and it would be 12 volts across here as well if we were to measure it. And then we need to calculate the current through R2. And if you remember, we were using this equation for current a minute ago. That would still work. We've got the voltage is 12, but the resistance, we're just looking at R2 this time. We're not looking at the total resistance, so that would be 10. So our current is 1.2 amps. The last question here, so the same resistors are now connected in series instead of in parallel. State how the following values compare with the parallel circuit. So the total resistance would increase. All this needs is words. We don't need to do any maths at all. So it would increase because when we put them next to each other, the resistance always increases. Therefore, the current, so current is opposite to resistance, is going to decrease because a higher current means it is harder, a higher resistance means it's harder for the current to flow. And then looking at our voltage, so we've got 12 volts coming in, and this is a series circuit, so it's actually going to split up across them both. So our voltage is going to decrease, whereas before it was 12 volts across both. And the reason is voltage is shared or split in a series circuit. Okay, question 4 is on the EM spectrum and waves. So we've got some bits of the EM spectrum written out there, but not all of them, but they are in order here. Radio waves are our longest, and they get shorter and shorter as we go to this end. So I always do that sketch just to help me picture what's going on. And then this describes the wavelength below. We've got 4 numbers, and we need to put them in order. You'll never have to memorize these numbers, but you will have to put these in order. So if we have a look at our picture, radio waves has got the longest wave, so it's got the largest wavelength, and this will have the smallest. So I'll just write that down to help us with our answer. We've got the largest, and we've got the smallest. So first thing I would do is look for the largest number, 4 times 10 to the power of 2. That's our biggest number. Then this one would be next, 2 times 10 to the negative 2. And then as we're going, this number, I know it feels like it's getting bigger, but it's becoming a larger minus number, so it's actually getting smaller. So next is our 3 times 10 to the negative 5, and then 5 times 10 to the negative 7. The next part is to name the missing regions, and you have to name all of the missing regions as well. So we've got UV, or you could write ultraviolet, X-rays, and gamma rays. But you get no mark, I'm afraid, if you do not do all of them, and there are 7 in our EM spectrum. Next one is to state what is meant by the term ionizing radiation. So I would say it is radiation that damages cells. You could have also said it removes the electrons from atoms or it interacts with atoms. For some reason on the mark scheme this year, it says do not accept just causes cancer and mutations. So you've got to be a little bit more specific, say it damages cells, or if you can remember what it actually does, which is remove the electrons from atoms, that would get you the mark as well. Part C, all waves are transverse. What else do they have in common? So they all travel at the same speed. In a vacuum, although you could get the mark just for saying they travel at the same speed. You could also say they all transfer energy. Part D is on satellites and the speed of signals travelling either through a satellite or through a cable. So we're going to be using speed is distance divided by time for this question, and we're going to be working out the time delay and working out which one has got a smaller or larger time delay, so which one travels faster. I know it says faster, which is a little bit confusing with the speed, because you might just think the higher speed travels faster, but it's got a different distance to go, so the time delay will be different. So the first thing I'm going to do, either using my formula triangle or not, is I'm going to rearrange, because we're working out time. So time is distance divided by speed. So first thing I'm going to do is I'm going to do that for the cable. Time is distance divided by speed. So the distance for our cable is 6 times 10 to the 6. And I'm going to divide it by the speed in the cable, 2 times 10 to the power of 8. And my answer is 0.03 seconds. So that is our delay for the cable. Then we've got the satellite. Again, we're doing the same equation, distance divided by speed. So our distance here is 7.2 times 10 to the power of 7, divided by the speed that it travels, 3 times 10 to the power of 8. And I should get the answer of 0.24 seconds. And that is actually our total distance. I know for satellites you've got to check, do we need to times it by 2? But no, that's our total distance. So that you get 1 mark for each of those. And then we've got to say which one travels faster. So Owen says it is faster by satellite. I'm going to disagree because the time delay is longer. You have to write agree or disagree to get all 3 marks here. Question 5 is about electricity use in the home, domestic electricity. So we've got 2 different kettles with different powers, different times to boil in minutes and in hours. So calculate the units in kilowatt hours by kettle B if it's used to boil 0.5 litres of water 6 times a day. That's an important part of the question. So 0.5 litres of water is already in our table, so we don't need to worry about that too much. And we're looking at kettle B. So the equation you need to look up in your page 2 is our units used is going to equal power times time. And you can probably work that out from the unit as well, because our unit is kilowatt hours, and we've got watts here, and we're going to use hours. So we have watts rather than kilowatts, so we're going to have to think about that. So our power for kettle B is 2,400, but that's in watts, so let's convert it into kilowatts. So we divide it by 1,000, so that's 2.4 kilowatts. So that would get probably your first mark somewhere there. And we're going to use power times time, so 2.4 kilowatts. We need to times it by the time in hours. Annoyingly, it's not given us the time in hours, but it has given it to us in minutes. So we'll do 2.5 minutes, but we're going to divide it by 60 to convert it into hours. Because there's 60 minutes in an hour. We also need to times it by 6, because we're doing it 6 times in the day, which gives you an answer of 0.6 kilowatt hours. Quite a hard question for 2 marks. Then we're going to use this answer in the next question. So again, we're showing our workings in case we got the answer wrong for the one before, so we can show we're doing it correctly. So first of all, we are doing it for 1 week. So we already are doing it 6 times a day, but 1 week we're going to times it by 7 to start with. That would give us the total units used, 4.2 units. And then we've got to work out the cost, so we're then going to times that 4.2 by our 34 pence to work out how much it's going to cost us in total, 142.8 pence. You do not need to round it, but if you do, make sure you round it correctly to 143 pence. So the next question is comparing the two it's quite challenging. So it's saying it would be cheaper to use kettle B because it's got a lower power. However, the cost of using something comes from the energy rather than the power. If you remember, energy is equal to power times time. So what we're going to prove is that they both use the same amount of energy by doing power times time for the both of them. It doesn't actually matter about our units or anything here because we're proving they're the same. So if I do A, and I'll do the power of 3,000 watts times by 2 minutes. And for B, I can do 2,400 times by 2.5 minutes. Both of these equations give you the same answer of 6,000. There isn't really a good unit because I've used strange units, but it's 6,000 of energy, so it's the same for both. Therefore, Sophia is correct, because when we're working out the cost of electricity, we do the cost per unit times by the units used, and the units used are of energy. So they are using the same energy for both. Part B is all about the ring main circuit in the home. So kettle B is connected into our ring main circuit and the diagram is shown below. So first thing you need to do is to state 2 advantages of the ring main circuit. So there are 4 possible advantages that you could choose between. So you could say the cables can be thinner. Each part of the cable has less of the current. That's because there's 2 pathways. Each socket has got 230 volts across it and can be operated separately. Or you could say that sockets can be placed anywhere on the ring. But make sure you've learned at least 2 of those in detail. And for the second part, the ring main is protected by an MCB. Give 2 advantages compared to a fuse. So it's faster or more sensitive than a fuse, and it can be reset, so doesn't need replacing. Last part here, the MCB is a rating of 32 amps and the maximum power is 7,360. Jack states all these appliances can be connected and used at the same time. Determine whether he's correct. So we need to add up all of these first because it's a space for calculation. I would write down your sum just to prove that you've done it correctly. And carefully type this into your calculator and check as well. And you'll get 7,750 watts, which is above the maximum amount. So he is not correct. And make sure you write that to get the mark. Question 6 is about a hydroelectric power station. The first part is asking you why we use a step-up transformer. So the first mark is for saying either it increases the voltage or it decreases the current. I would write both because you don't know what the mark scheme is going to say. And the reason we do it is to reduce the energy loss due to heat in the wires or to increase the efficiency. For this next part, we have a voltage. We want us to calculate a current, and we also have a power here as well. So we're working out a current, and we're going to look up, first of all, what equation we're going to use. Power is voltage times current, and we're going to rearrange it using a formula triangle if you like. So we put the I and the V at the bottom. And to work out current is going to be the power divided by the voltage. So the power is 1,800 megawatts. That's times 10 to the power of 6. You can check your formula sheet if you're not sure. And we're going to divide it by 400 kilowatts, which is times 10 to the power of 3. And that should give you the answer of 4,500. Make sure you write your workings. If you didn't do times 10 to the 6 and times 10 to the 3, you would have got a slightly different answer that would have had a 4 and a 5 in it, maybe 4.5. You'd have still got 2 out of 3 marks. The last question, part B. The graph shows how the power demand varies throughout the day in March. Use the graph to state what times we pump the water back to the top. The key bit here is knowing that we pump it back to the top when we have excess power, so people are not using it. So we're looking for the lowest bit of our graph. So you can get the marks for saying between 0 and 6, between 1 and 5, 1 and 6, 0 and 5, anything that describes this area roughly. And the second mark is for saying when the demand is the lowest, not just low, it's got to be the lowest on the graph.